All right, everyone, section 2.3, continuity. I recommend that you pause the video and draw what I've got going on here. An asymptote at x equals -3. There's a removable discontinuity, also known as a hole, at 1, 1. And then we have an asymptote, again, at x equals -4. So take a minute to draw that. Okay, so notice that when I was telling you what this hole was, I called it a removable discontinuity. Overall, this graph is discontinuous. The most generic way to look at that is I have to pick up my pencil to draw the whole thing. I have my branch, I have to pick up my pencil or my pretty pink pen, and I can draw this cubic-esque graph, and I have to pick up my pen in order to get the remaining graph. This does not mean that this graph is discontinuous everywhere. You can be continuous along a certain interval. So for example, the interval x is -3 to 1. So that would be x is -3, not included, open parenthesis, to 1, not included, open parenthesis. Between -3 and 1, this graph is continuous. From 1, 2, 3, 4, from 4 to infinity, this graph is continuous. In order to be a continuous function or to be continuous over an interval, the limit as x approaches some constant from the left of the function must be equal to the limit as x approaches that constant from the right. Now remember, the left-hand limit can exist and the right-hand limit can exist, but they're not necessarily the same. So a little side note here, if I'm approaching at 4, if I'm approaching 4 from the left, the limit is -infinity. If I'm approaching 4 from the right, the limit is +infinity. Okay, so those are not the same. And if a function is going to be continuous, they have to be the same. So this must equal the overall limit, which must equal the exact value. So let me draw a really quick, an example that where this might be true, the right might equal the left, and the overall limit might be the same, but the exact value doesn't exist. So if I were to leave this branch here on the right, so if my graph looked like the branch here on the right and the branch on the left, okay, this limit exists. The right hand is approaching infinity. The left hand is approaching infinity. The limit is the same. The overall limit exists, but the exact value does not. So it is possible that the right hand equals the left hand equals the overall, but yet the function is still considered discontinuous. Okay, so your book has this wonderful thing called the intermediate value theorem. So if you remember, I wrote so sloppily, sorry. So from -3 to 1, we said that, from here to here, we said that the function was continuous. Okay, well that's what the intermediate value theorem says. The intermediate value theorem says you have some point A and B, and they have values, they have exact values, so the f of A exists and the f of B exists. In order to be continuous on that interval, there is some value C, which is in between A and B, hence intermediate. You have some value C in between A and B such that no matter where that value of C is, its exact value exists. So for any point C between A and B, so maybe C is here. Maybe C is there. For every single value that you pick, for every value that you pick for C, the exact value must exist, and that's the intermediate value theorem. Okay, average rate of change. I'm going to try and cover this up here. What's average rate of change? Yes, average rate of change is also known as slope. So when you very first learn slope, y2 minus y1 over x2 minus x1, and it doesn't matter the letters you use. It could be b2 minus b1 over a2 minus a1, fine. But then we start using more, grown-up math terms. A, f of a, x, f of x, and you might recall we did some of this like way in chapter 2 of the trig book. Rate of change, the f of x minus the f of a over x minus a. This is this is slope. This is slope, different letters. So slope represents change. So, do you remember Phoebe and her rocket ship? Remember she, for those of you who had me or Miss Lou, how she put her retro rocket into super boost and then she bounced off the planet of Mars. So, you hopefully remember her. She was pretty awesome. Okay, I drew a graph here. See, I said Phoebe. Time and total distance, and I just drew a generic graph. So here's what we have to be careful about with rate of change. If this is some point A, f of a, so this is, let's say, after 2 minutes, Phoebe has gone 6,000 miles. And then I do some value x and f of x. So then after 4 minutes, she's gone 17,000 miles, as only Phoebe can do. If I ask you Phoebe's average rate of change between A and x1, this average rate of change, the slope between these 2 points, if I have a point here and a point here, this slope is relatively small, and I misspoke. She should have gone 2 seconds, 2 miles, 10 seconds, 10 miles. This is where she kicks it into high gear. This is where the retro rocket comes out. If I ask you to find the rate of change between when she first fires the rocket until she gets to be, to a certain point, let's say here, this slope is much, much larger. So Phoebe's speed between x1 and x2 versus her speed between A and x1 versus her speed between A and x2, these are all different. So you have to be careful with average rate of change, and we're going to talk about this extensively. Her average rate of change is very specific between 2 points. Her average rate of change is specific to 2 points. Well, which 2 points are you choosing? Are you choosing like a marathon runner, right? A marathon runner's speed, right? How many miles they're going per minute is very different in the beginning of the race versus at the end of the race. So we're going to be talking extensively about this, but I just wanted to give you just a generic, here's rate of change. It's specific to 2 points. Those 2 points are going to change, haha, no pun intended, depending on the time interval that you're looking at. All right, you guys, I will see you at office hours today if you choose to come.